Welcome to the Explainer. Today, we're jumping right into decoding the universal language of maps. We're talking about the absolute building blocks of location. No fluff, just exactly how we translate the real world onto a page. Let's get into it. Okay, let's dive into this. Before we even attempt to wrap our heads around mapping the entire spinning planet, we really need to nail down the 5 fundamental elements of any flat 2D map. Think of these as the map's basic vocabulary. First up, the title. It tells you exactly what you're looking at, right? Like population density or average annual rainfall. Second, you've got the legend, or the key. This decodes the colors and shapes for you. Like a tiny star might mean a capital city, or a green blob is a forest. Without a legend, you're just staring at meaningless shapes. Then there's the border. It frames everything, keeps it clean, and tells you exactly where the mapped area stops. And finally, symbols. These are those simple little icons, a tiny airplane for an airport, a little H for a hospital, that make the map readable without cluttering it up with a bunch of messy text. Now, out of those 5, there's one element that deserves its own spotlight, and that's scale. Scale is, honestly, the magic ingredient here. It's what takes a massive, real-world distance and shrinks it down so it fits on your screen or a piece of paper. For example, a scale might tell you that 1 single centimeter on the map equals 10 entire kilometers on the ground. Or it might be a ratio like 1 to 50,000. This is incredibly powerful. It's the only reason you can accurately measure distances or figure out how long a road trip will take. It literally shrinks the world so you can hold it in your hands. So that works perfectly for flat paper. But how do we transition to reality? Because, as we all know, the Earth is definitely not flat. It's a giant, slightly squished ball floating in the vacuum of space. And here's the catch with the sphere. There's naturally no top, no bottom, no left, and no right. So how on earth, literally, do we orient ourselves? How did early navigators actually decide which way was up? Well, to make navigation possible at all, humans had to just invent imaginary reference points from scratch. Step 1 in building this global system is nailing down a top and a bottom. Picture this. Imagine taking a regular ball and just shoving a pencil straight down through the very top until it pokes out the bottom. That point where the pencil goes in at the top, that is what we call the North Pole. It's sitting exactly at 90 degrees north. If you were to stand right on that spot, literally every direction you look is south. It's wild to think about. And conversely, where the pencil comes out the bottom, you have the South Pole at 90 degrees south, right in the middle of Antarctica. Stand there, and everywhere you look is north. These 2 points give us our absolutely crucial vertical anchors. Now, what about that pencil we just imagined pushing through the ball? That represents the Earth's axis. It's an invisible, imaginary rod running straight through the center of our planet, connecting the North and South poles. And this is vital to our daily lives. The Earth is constantly spinning or rotating around this invisible axis, making one full turn every 24 hours. That spin is exactly what gives us day and night. Without it, we wouldn't have sunsets, sunrises, or any of the rhythmic cycles we rely on. It defines our days, and it gives us the perfect starting point to map out the rest of the planet. Okay, so once we have our top and bottom anchors, we need to split the Earth right down the middle. Imagine taking an apple and slicing it perfectly across its widest part. That imaginary cut represents the equator. It's a circle wrapped right around the middle of the Earth, sitting exactly halfway between the 2 poles. Because it's our primary baseline, the equator gets assigned the value of 0 degrees, and it neatly chops the planet into 2 equal halves, which we call hemispheres. Hemi meaning half, sphere meaning ball. Everything north of this line is the northern hemisphere. So, North America, Europe, most of Asia, and everything south is the southern hemisphere, like Australia and most of South America.
And this brilliantly illustrates the concept of latitude. If the equator is that first band around the middle, imagine snapping a bunch of horizontal rubber bands all around the globe, stacking them up toward the North Pole and down toward the South Pole. Notice how they all stay perfectly flat and horizontal. Because they never, ever touch each other, we call them parallels. Latitude is simply measuring how far north or south you are from that 0-degree equator line. It goes all the way up to 90 degrees at the North Pole and down to 90 degrees at the South Pole. So latitude, it's just your north-south position.
But here's the thing, just knowing how far up or down you are doesn't really pinpoint you. We also need to know your left to right or east to west position. And that is where longitude steps in. Now forget the horizontal rubber bands. Instead, imagine peeling an orange. You know how the peel naturally divides into those vertical wedges, and every single slice meets at the very top and the very bottom? That is exactly how longitude lines or meridians work. They run north to south, pole to pole.
They start their measurement at another imaginary line called the prime meridian, which runs straight through Greenwich at 0 degrees. From there, they measure how far east or west you are, up to 180 degrees either way. And the key difference here? Unlike latitude, all longitude lines eventually crash into each other right at the poles. Now, people mix these two up all the time, but I've got a foolproof memory trick for you. Think of latitude like climbing a ladder. The rungs of a ladder run horizontally, and you use them to go up or down, north or south. Plus, lat sounds kind of like ladder, right? Then, think of longitude as taking a long journey horizontally around the Earth, moving east or west. The lines themselves are long, stretching vertically from the absolute top of the planet to the bottom. Keep those two vivid images in your head, the rungs of a ladder and a long journey around the equator, and honestly, you'll pretty much never confuse them again. Let's just pause for a second to lock in these technical differences. With latitude, the lines themselves are drawn east to west, but they actually measure your north-south position. They're parallel circles that never touch, starting at 0 degrees at the equator. Now, for longitude, the lines are drawn vertically, north to south, but they measure your east-west position. They're half circles that always collide at the poles, starting at 0 degrees at the prime meridian. By mashing up a latitude value with a longitude value, we're basically using a 360-degree circle to describe literally any spot on a spherical planet. When you overlay those horizontal rubber bands and those vertical orange slices, you get what we call the global grid. It's essentially the Earth's master XY coordinate system. Think of it like a perfectly planned city grid. The horizontal streets are your latitude, say 1st Street, 2nd Street, moving north. The vertical avenues are your longitude, Avenue A, Avenue B, moving east. If a friend says, hey, meet me at the intersection of 5th Street and 8th Avenue, you know exactly where to go. A latitude alone? Useless. A longitude alone? Also useless. But cross them together and they give every single place on Earth one precise, unique address. So the crucial point is how we actually apply this in the real world. Let's look at the exact coordinates, 33.7 degrees north, 73.1 degrees east. What does that actually mean? Well, it means you start at the equator and climb 33.7 degrees north up our imaginary ladder. Then you jump to the prime meridian and travel 73.1 degrees east on our long journey. The single exact pinpoint where that specific latitude line crosses that specific longitude line, that is the city of Islamabad. Every city, every mountain peak, every cargo ship in the middle of the ocean, and literally the chair you're sitting in right now has a pair of numbers exactly like this. And just like that, we've gone from the basic 5 elements of a flat 2D map to constructing a fully 3D coordinate system using poles, axes, rubber bands, and orange slices. You now know exactly how this universal language works. So as we wrap up this explainer, I want to leave you with a thought. Latitude and longitude form this massive, invisible net cast over our entire globe, connecting everything. Take out your phone, open up whatever map app you use, and ask yourself, what are the exact imaginary lines intersecting precisely where you are sitting at this very moment? Look up your own coordinates. Once you do, I guarantee you'll see your place in the world in a completely new way. Thanks for hanging out with me on this explainer, and keep exploring.